So we're going to use the reflectance map because we know the source direction and we know the reflectance properties. But as we discussed earlier, we need additional assumptions or constraints to solve the shape from shading problem. We cannot take a single intensity value and figure out what the surface orientation there is. So let's start with our first constraint. And that is related to occluding boundaries. So here is an object, it's a curved object such as this. And when you take an image of this object, you may get an image that looks something like this. And this white line that you see here is called the occluding boundary. It's where the object curves upon itself. It's curving away from the viewing direction. So if you look at an object such as this, you're talking about this being the occluding boundary where the surface normal goes away and then turns around, and so it's curving away from the viewing direction, which is the camera right here. So for these points, there's an interesting constraint that we can use, which is that we know that there are surface normals in 3D that are going to lie along the occluding boundary. And let's consider one of these surface normals, this one. Well, this surface normal we know is going to be perpendicular to the viewing direction because the object is curving away from the viewing direction of the camera. And we are also assuming that the viewing direction is the same for all points in the scene. So we know that N is perpendicular to V. So we can say N is perpendicular to V. Now let's say that you take this image that we're talking about here and we apply an edge detector to this image. And we find all the edges on the occluding boundary. So let's say you take this one edge right here, E. We know that corresponds to an edge in 3D as such. And we know that this edge is perpendicular to the normal as well. So N is perpendicular to E. So we know this edge in 3D because we know that the image plane is perpendicular to the viewing direction of the camera. So we can, just from the two dimensions, the two components of the edge in the image, we can write the edge in 3D because it happens to lie in the image plane. So you have N perpendicular to E. So N is perpendicular to V and N is perpendicular to E, and we know E and V, and therefore we can compute the surface normal at any point on the occluding boundary as simply the cross product of E and V. So what we're going to do is essentially compute the surface normals on the occluding boundary, and we're going to use these as boundary conditions to solve the shape from shading problem. As we compute the surface normals at other points in the image, we're going to hold these surface normals constant. All right, so that's one of our conditions or constraints. And then we have the most important constraint. This is a fundamental constraint, which is called the image irradiance constraint. And that's basically telling you that whatever FG value you compute at a pixel, when you plug that into your reflectance map, which you've pre-computed, you should get an intensity value which is equal to the intensity value that you measured at that pixel. The pixel being represented as XY right here. So what we're saying is that let's assume for a minute you've computed FG values at all points in the image, then the difference between the intensity you measure at a point minus the reflectance map value estimated using the measured or estimated FG values, that should be 0. And so we're going to subtract these two and square it, integrate it over the entire image, and we want that error to be as small as possible. We want to penalize that error. In other words, we want to find FG values that make this error as small as possible. That makes complete sense. That's just the most fundamental constraint we have, which is the image irradiance constraint or the image intensity constraint. All right, and now we need to throw in one more constraint. Remember, thus far, all the constraints we have to do with individual pixels or points on the surface. And we know that there is no hope of solving the shape from shading problem if you treat each point independently. We have to somehow tie these points together. We have to couple them so that we can propagate their values and have them constrain each other in some ways. And the assumption we're going to make is that the surface is smooth. So the object surface is smooth. What that means is that in terms of Fg values, F and G are going to change slowly over the surface. That's what smoothness really means. So we're going to throw in one more term here, which ensures that F and G vary slowly. That means the surface is smooth. What we do is that we take the first derivative of F with respect to X, F with respect to Y, G with respect to X, G with respect to Y. We're going to square all of those, add them together, integrate that over the entire image, and we want that error, which is ES, S for smoothness, to be as small as possible. That's going to penalize rapid changes in F and G. And the purpose it serves for us is that it ties the Fg values of neighboring pixels together in a way that we'll see soon. All right, so now we are ready to formulate our shape from shading problem. What is the problem? We're going to say that we have an error that we want to minimize. We want to find the Fg values at all points in the image that are going to minimize this error. And this error has two components, a smoothness constraint term and the image irradiance error term. So we have these two terms, ES and ER, and we can weight them using a constant lambda right here. Lambda is useful because what we can do is if our image intensity measurements are very accurate, let's say it's a noise-free sensor, and you get very good measurements of image intensity, then you're going to give more weight perhaps to your image irradiance constraint, which is ER. And ultimately, we're actually going to develop an iterative algorithm. And in this iterative algorithm, once the Fg values begin to evolve, you can start increasing lambda so that more emphasis is placed on your image irradiance constraint, and you start relaxing your smoothness constraint. And in doing all of this, in minimizing E and finding F and G, you're going to use the known Fg values on the occluding boundary of the surface. We're just going to hold those constant. So that's the algorithm that we're going to now discuss. It was developed by Ikeuchi and Horn, and it's called numerical shape from shading. Now, all the terms that we have talked about, the error terms and the constraints, we've done all of this in continuous domain, but we know that the image we're going to deal with is a discrete image. So we've got to map this, our constraints to the discrete domain, and that allows us to now develop our numerical shape from shading algorithm. So this is how it works. Let's start with the smoothness error to start off with. The smoothness error at the point or pixel ij is ESij. And that, as you remember, includes the derivative of f with respect to x, the derivative of f with respect to y, and the same for g. And so this term that you're seeing right here is the difference between the f value at ij and its neighbor in the x direction. This is the f value at ij and the difference between that and the neighbor in the y direction. And then you're going to, so this is fx and this is fy. You're going to do the same with g. So you get these four terms, you square them up, and that's going to be your smoothness error for the pixel ij. And now we can do something similar with your image irradiance error. So in that case, you have the image irradiance error ERij equals to the difference between the intensity you measured at that pixel, and let's imagine for now that you have computed f and g values of that pixel. If you plug that into the reflectance map, whatever intensity you get there, those two should be as small as possible. So that's your image irradiance error right here. You square that. So we're going to add up these two. So your final error is going to be the sum of these two errors. And remember, we have this weighting function here, lambda. And you're going to sum those errors for all pixels in the image. And that's what these two summations are right here, over I and over j. So in other words, we want to find the Fij and Gij values that minimize E. That's our problem. So what we're going to do here is change variables and use FKL, GKL, because we want to focus on one particular pair of FG values at the pixel KL. If FKL and GKL minimize E, then the derivative of E with respect to FKL is equal to 0, and the derivative of E with respect to GKL is equal to 0. So now we can sort of see what the problem with shape from shading is. If you're given an image which is n by n, then you have n squared intensity values. Those are your measurements, your givens. Unfortunately, we have two n squared unknowns. So essentially, you have n squared unknowns for f and n squared unknowns for g, so two n squared unknowns. So in shape from shading in general, you have 2 times the number of unknowns as you have knowns. That's what makes it an interesting, challenging problem. But there is hope. And the hope comes from the fact that let's say you take one particular pixel ij, the fij and gij, these two numbers, show up in only 4 terms in this summation over the entire image that's shown right here. In other words, fij and gij will appear twice in the term that corresponds to that pixel ij itself in E. They will appear once for this pixel, the term corresponding to this pixel on top, and this pixel to the left. So that's the saving grace here, that even though you have a summation over the entire image, if you take any one pair of f and g, that is fkl, gkl, that's going to appear in only 4 terms. So you can write out those 4 terms and then find these 2 derivatives that we discussed right here and set them equal to 0. So that's what we do. We write out those terms, and when you find the derivatives and set them equal to 0, you get this expression right here. So let me just briefly describe what's going on here. You have fkl right here. You have f bar and g bar. F bar and g bar, by the way, are the average values of f and g. The average is computed over the 4 neighbors to the pixel KL. The neighbor on top, bottom, left, and right. So that's what these are. So that's f bar, which is the average of these 4 values, neighboring values, g bar, average of these 4 neighboring values. That's what these 2 are. Then you have lambda here. You have IKL, which you have measured, the intensity value at that pixel, minus the reflectance map value at FKL, GKL. And so we can, if we have a value for FKL and GKL, we can plug that into the reflectance map and get the value of the reflectance map. And then you also end up with the derivative of the reflectance map with respect to F, computed at FKL, GKL, and the derivative with respect to G, computed at FKL, GKL. So you can see that the FKL and GKL do appear here, but they're embedded within the reflectance map as well as the derivative of the reflectance map, and that's what makes this a challenging problem. There's no single shot closed form solution to this, to finding FKL and GKL. So this is how we tackle it. This is where the trick comes in. What we do is we move FKL, GKL, which is right here, to one side of the equation and keep everything else on the other side. And then what we do is we have this superscript right here. We throw an n plus 1 on top of FKL and GKL, and we throw an n on top of everything else on the right-hand side. N is not an exponent here. It's the iteration number. So what this means is that, let's imagine for a minute you start with some FKL, GKL values. You use all of those values on the right-hand side, and now you can compute everything on the right-hand side. And that gives you a new set of values for FKL and GKL on the left-hand side. And that would be n plus 1. You're going to do that for all the pixels, compute the entire set of F and G values over the image, and then you're going to do the same thing. Use them to recompute the right-hand side, and then you end up getting new values for F and G on the left-hand side. This is what makes it an iterative solution. So the one thing that I should emphasize here is that when you start the iterations, you can use 0, 0 for all the fg values, except the fg values on the occluding boundary, which you happen to know. These are very important. If you set everything to 0, 0, it's quite possible that the algorithm is just going to be stuck where it is. It'll just tell you that the fg values at all pixels are 0, 0, and it just gets stuck there. But since you have non-zero values in the occluding boundary, and you're going to insist on keeping them the same, those values are going to start getting propagated into the insides of the object. And slowly, the f and g values will then begin to converge. That's the hope here. So you're going to use the known normals to fix fg on the occluding boundary. You can perhaps initialize everything else to 0, 0, and then you iteratively compute fg until the solution has converged. What do we mean by convergence here? It's when the fg values at all pixels cease to change. They all arrive at a solution and stay there. So that if the difference between the fg values in consecutive iterations is very small at all pixels, then basically you can assume that you have converged. So now let's take a look at a few examples. So here is a synthetic object. So this is a synthetic example, a Lambertian vase. And in this case, when you apply your algorithm, you're going to then end up with fg values over the entire image. And then you're going to then use the technique we used for photometric stereo to go from surface normals to a continuous surface. That's the integration problem. So when you do that, you get a shape that looks like this. So this is a very simple example. It's a very well-behaved surface, so to speak, and it's also a synthetic example, and you get a nice reconstruction. Here's another one, also synthetic, but in this particular case, we're taking a more complex depth map and then shading it using a known reflectance value, Lambertian, and then you apply the algorithm. But in this case, you have some dramatic changes in surface normal at some points right here, maybe around the nose and so on. And that leads to some errors. You get something that looks like the bust, but at the same time, you see some errors here as well because you're violating some of the assumptions that we've made, such as smoothness. Now let's take a look at some real examples, real images. So here is a real image of a scene, and I would say that you get a very nice reconstruction. This is, again, with the known source direction and the Lambertian assumption. You get a reconstruction that looks pretty good. By the way, the reflectance doesn't have to be Lambertian. It can be some other reflectance function as long as you know it. Now, of course, this doesn't work at all for highly specular objects, mirrors, say, for instance. You're not going to get shading of the type that we're talking about here. And here's another example of a human face. And in fact, shape from shading algorithms have evolved quite a bit and now can also handle albedo changes or reflectance changes over the surface, which you can see in the case of the eyebrow area, say, for instance, here, but you end up with a fairly nice reconstruction. So, shape from shading is a fundamentally hard problem, and I would say that any result that you get that is fairly close to the actual shape of the object is impressive in this case because it's one of those very difficult recalcitrant problems, and the only reason we've been able to solve this is by using these assumptions which we've mapped to constraints and also using an iterative solution.